The moral is that Bayes nets tend to be the most compact and thus the easier to do inference on when they're written in the causal direction. That is, when the networks flow from causes to effects. Let's return to this equation, which we use to show how to do inference by enumeration. In this equation, we join up the whole joint distribution before we sum out over the hidden variables. That's slow because we end up repeating a lot of work. Now we're going to show a new technique called variable elimination, which in many networks operates much faster. It's still a difficult computation, an NP-hard computation, to do inference over Bayes nets in general. Variable elimination works faster than inference by enumeration in most practical cases. It requires an algebra for manipulating factors, which are just names for multidimensional arrays that come out of these probabilistic terms. We'll use another example to show how variable elimination works. We'll start off with a network that has three Boolean variables. R indicates whether or not it's raining. T indicates whether or not there's traffic. And T is dependent on whether it's raining. And finally, L indicates whether or not I'll be late for my next appointment, and that depends on whether or not there's traffic. Now, we'll put up the conditional probability tables for each of these three variables. And then, we can use inference to figure out the answer to questions like, am I going to be late? And we know by definition that we could do that through enumeration by going through all the possible values for R and T and summing up the product of these three nodes. Now, in a simple network like this, straight enumeration would work fine. But in a more complex network, what variable elimination does is give us a way to combine together parts of the network into smaller parts, and then enumerate over those smaller parts, and then continue combining. So we start with a big network, we eliminate some of the variables, we compute by marginalizing out, and then we have a smaller network to deal with. And we'll show you how those two steps work. The first operation in variable elimination is called joining factors. A factor, again, is one of these tables. It's a multi-dimensional matrix. And what we do is choose two of the factors, two or more of the factors. In this case, we'll choose these two, and we'll combine them together to form a new factor, which represents the joint probability of all the variables in that factor. In this case, R and T. Now, we'll draw out that table. In each case, we just look up in the corresponding table, figure out the numbers, and multiply them together. For example, in this row, we have a positive R and a positive T. So the positive R is 0.1, and the entry for positive R and point T is 0.8. So multiply them together, and you get 0.08. Go all the way down. For example, in the last row, we have a negative R and a negative T. Negative R is 0.9. The entry for negative R and negative T is also 0.9. Multiply those together, and you get 0.81. So what have we done? We use the operation of joining factors on these two factors, giving us a new factor, which is part of the existing network. Now we want to apply a second operation called elimination, also called summing out or marginalization, to take this table and reduce it. Right now, the tables we have look like this. We can sum out or marginalize over the variable R to give us a table that just operates on T. So the question is to fill in this table for P of T. There'll be two entries in this table, the plus T entry, formed by summing out all the entries here for all values of R for which T is positive, and the negative T entry, formed the same way by looking in this table and summing up all the rows over all values of R where T is negative. Put your answers in these boxes. The answer is that for positive t, we look up two possible values for r, and we get 0.08 or 0.09. Sum those up, get 0.17. And then we look at the two possible values of r for a negative t, and we get 0.02 and 0.81. Add those up, and we get 0.83. So we took our network with RT and L, we summed out over R. That gives us a new network with T and L, with these conditional probability tables. And now we want to do a join over T and L and give us a new table with the joint probability of P of T and L. And that table is going to look like this. The answer again for joining variables is determined by pointwise multiplication. So we have 0.17 times 0.3 is 0.051 plus T and plus L. 0.17 times 0.7 is 0.119. And then we go to the minuses. Minus 0.83 times 0.1 is 0.083. And finally, 0.83 times 0.9 is 0.747. Now we're down to a network with a single node, TL, with this joint probability table. And the only operation we have left to do is to sum out to give us a node with just L in it. So the question is to compute P of L for both values of L, positive L and negative L. The answer is that the positive L values, 0.051 plus 0.083 equals 0.134, and the negative values, 0.119 plus 0.747 equals 0.886. So that's how variable elimination works. It's a continued process of joining together factors to form a larger factor, and then eliminating variables by summing out. If we make a good choice of the order in which we apply these operations, then variable elimination can be much more efficient than just doing the whole enumeration.